We're going to talk today about chemical calculations. Specifically, we're going to talk about mass volume calculations. Alright? So we've been dealing with mass calculations, and we've been talking about mass to moles and moles to mass for a large variety of equations that we've been doing. Today, we're going to look at what happens if we introduce volume into our calculations. The concepts remain exactly the same. We're going to go from mass to moles, and then from moles to volume. Okay? Or we're going to go from volume to moles, and then from moles to volume. So let's introduce some of the equations that we were dealing with that we can actually use for this. Now we have been using number of moles is equal to mass over molar mass. Yes? Okay? A previous equation that we learned when we dealt with volume was something related to, we didn't do an equation, but we looked at what happens with molar volume. Do you remember that? We spoke about molar volume. And molar volume was the volume that 1 mole of any gas would occupy. So 1 mole of any gas at STP. Do you remember this? STP standing for standard temperature and pressure. So 1 mole of any gas at STP will occupy a volume of, do you remember the number? It's 22,4 decimeters cubed. Okay, so that is the amount of space that 1 mole of any gas will occupy at STP. The equation that we can use to calculate molar volume or moles says that number of moles is equal to volume over molar volume. Okay? Where N refers to number of moles, V refers to volume given, and Vm refers to the molar gas volume constant. The molar gas volume constant, which is the 22,4 decimeters cubed. Okay, so that is what we're going to start using now. We're going to pause. Alright, what we're going to do now is we're going to do an example. Okay? So the example that I would like to use is, let's use a sulfur dioxide example. So let's say we have SO2, which reacts with oxygen, and we form SO3. And we're going to balance first. So no, I'm wrong. Just hold on. Yes, that's good. Okay. So we have our balanced equation. Yes? Do you agree? No? Yes. You do agree? Okay, good. So we have our balanced equation, and what we're going to do now is we're going to do the same rules as what we did before. So we start off with a mole ratio. So our mole ratio is 2 parts to 1 part to 2 parts. We're good. Okay. And then the question will read as follows. The first thing that I'm going to do is include the phases. Now the phases mean whether things are solids or liquids or gases. Okay. G stands for gas. L, so G is for gas. L is for liquid. Okay. S is obviously for solid. And when you see AQ, it means in solution. Alright, aqueous, in solution. So it means something's been dissolved in something else. Now, if there's a gas in my balanced equation, then it means that I can use molar volume for that particular substance. Okay? Remember when we did molar volume, we said we must remember that this only relates to gases. It's a really big deal. We can't use the equation, we can't use the constant unless we are dealing with a gas. Okay? So if we're dealing with a solid or a liquid or a solution, we can't use it. And I can't mark it, just so you know, I can't mark it because it means you made a very big mistake. So here, this is what we're going to do. We're going to say that if, for this question, if I am given 8 grams of sulfur dioxide, what volume of oxygen gas will be necessary? What volume of oxygen gas will be necessary to react with 8 grams of SO2? Okay. Let's look at what we're going to do in terms of my method. We're going to start off the same way we usually would. We're going from mass to moles. We're going to use the ratio, and then we're going to go from moles back to volume now. Okay. So, my number of moles is going to be equal to the mass given over the molar mass of the substance. The mass given is going to be 8 grams. Agreed? The molar mass is going to be the sum of all the parts of this formula. Do I involve the 2 in the front? No, because the 2 in the front relates to the ratio. We use the 2 in the front when we deal with the ratio, not when we calculate the molar mass. So I have sulfur, which is 32, and I'm adding that to 2 times my 16. So it's 32 plus 32, which gives me 64. So it's 8 divided by 64. Somebody check my maths, please. Just somebody check my maths and my numbers. And then somebody do 8 divided by 64. 1,125. Did I get the molar stuff right, guys? Yes? Okay. So 0.125 moles is my number of moles ready. Okay? That's 2 moles. Let's use the mole ratio from this point to that point over there. The ratio is 2 to 1. What must I do? Divide by 2. Everybody on the same wavelength? Yes? Okay. If I divide this by 2, what do I get?
0.065.
Nice. 0.0625 moles. Because we're dealing with a mass to volume calculation. Back on the mass to moles, ratio, moles, back to volume. I'm going to use the equation that I just put up on the board. The one that says the number of moles is going to be equal to the volume that I have over the molar volume. Okay? I have the number of moles. I have Vm because that's a constant. Okay? Which means that I can calculate the volume that will be produced. I'm going to rearrange this. So I'm going to say V is equal to N times by Vn. So that's 0.0625 multiplied by the 22.4, and that gives me an answer of 1.4. And what is volume measured in this instance? Deciliters cubed. 1.4 deciliters cubed of oxygen will react with 8 grams of sulfur dioxide. It's not too bad. It's just using another equation in the mix. Okay? So we're good. Let's pause.